All right, guys, we're going to go through section 7.4, which is about arc length. And I promise it's not as bad as volume. Okay, so what we're doing is posing the question of how long is a curve? Okay, so we have done extensive research into how to find area under a curve. And we obviously have done a lot with volume of three-dimensional functions created by curves. Now we're going to ask, how could you measure the length of a curve? Okay, so kind of like if you have a function and you took a piece of string and laid it on top of the function, how long would the string be? So we're going to do that by first looking at like an estimation trick. So let's say we have a shape that's round or curved, and obviously mathematically we don't really have we haven't yet established ways to find distance in a curve or a shape that's curved other than a circle. So what we could do is instead find small lengths of straight line segments and use that as an approximation technique. So, for example, if I said, let's find the length of this parabola from -2 to 2. What we could do is we could find the distance from a couple points to a couple of different points to each other using the distance formula, right? So we could say, what's the distance from here to here, and then here to here, and then add all these up. So that would be an okay way to do it. And obviously it would get even more accurate if you could add a bunch of tiny lines. So distance of this little line, and then that one, and then that one, because the smaller the line, the more accurate your solution would be, right? Okay. But honestly, I'd rather not do that because adding up and doing the distance formula that many times is going to get extremely tedious. Luckily, there is a way to avoid doing all that extra work. So we're going to figure out how that would look. So let's think about what it would look like if I said find the distance between two line segments. So I've got it zoomed in here. Here are your two line segments. And the distance between them is basically like a play on Pythagorean theorem, which you know as the distance formula. For most of you, this is not the traditional way to write the distance formula. Most of you are going to be more familiar with something like x2 minus x1 quantity squared plus y2 minus y1 quantity squared. But I'm asking you to look at it in the first format because it's going to help us with our development of this formula. So instead of x minus x, I'm going to call it change in x and change in y. So this is just saying, let's take the distance formula. That's how you would find the distance between 2 points. But we're going to do that for all those little lines. So I need to say, let's add up the distance of all the little lines. Remember that big E there is the symbol for summation. Okay. So basically we're saying that if we wanted to take the sum of the distance of all those little lines, we would have the arc length if those lines were infinitely small. But remember that taking the sum of a bunch of things is the same thing as taking the integral, okay? The sum of a bunch of things is the same thing as taking the integral. Down here is the definition that reminds you of that, FYI. Just another side note, an integral is a powerful machine like summation on steroids. It does not merely just find the sum over the values for a particular tiny value of dx. It considers the limiting value of such a sum. So basically, if you're doing the limit as something is getting infinitely large, and that is adding up a bunch of things, then the integral can be used. Okay, now here's how the development of our formula comes to be. So back to the original question, what is the arc length of this curve? So we've already established we can use the integral, and inside the integral we have the distance formula, okay? Now some algebra has to happen in order to make this work. Step one, establish that this is the curve y equals x squared. Step 2, take the derivative, which would be dy dx, and that would equal 2x. Okay? Then you're going to multiply by dx, and so what you're going to end up with is that dy is equal to 2x dx. Okay? Now in this particular question, we could take dy, the thing we just found, and we could plug that in right here. So then that would give us the square root of dx quantity squared plus 2x dx quantity squared. Okay? The next thing you're seeing from this step down to the next one is factoring. So what happened here is that we see, okay, both terms have dx quantity squared. So we're going to pull that out, and it's just put at the end instead of the beginning. And if you take out a dx squared, you would have a 1 in its place, and then here you would have a 2x, and you do have to attach the squared to that. Now, the last step, from the middle to the last, what has happened is we see that this square root is over top of every single item, right? Well, if you were to just take the square root of dx quantity squared, you could just say that that's equal to dx, okay? That step is a very important one because that is what creates a function that can actually be integrated. Because in order for an integral to actually compute correctly, you do have to have a command at the end that tells it how to do that. So this is the command at the end telling it to integrate with respect to x. Okay, so here's what we're going to be integrating inside this radical. All right, so that leads us to a formula for arc length. So in the arc length formula, you are integrating from a to b, wherever you're kind of zooming in on your function, and that is the square root, which comes from the distance formula, and it says 1 plus f prime of x quantity squared. So if I go back and I show you again, 1 plus this thing, 2x, was the derivative, so f prime of x quantity squared, seems to make sense. And then you have dx at the end. Another way that you could write it, if you wanted to use, just a different notation for f prime of x, is you could call it dy dx. So really, we're just kind of following a formula for, a function. It's not really that difficult. So yay, let's take a look and see what an example might look like. So we have this, it's called a semi-cubical parabola, which is fun. And we are going to tell the arc length from 1, 1 to 4, 8. So before I write an integral, I think the first thing that I want to do is get this ready to plug into my arc length formula. And what I mean by that is by finding f prime of x or dy dx. Now, in order to find dy dx, I'm going to have to get y alone. So I think the way that I want to do this, I don't want to mess anything up. I think what I want to do is raise each side. Let me do it this way. Raise each side of the problem to the 1/2 power. Okay, so if I raise the left side to the 1/2 power, that means I would multiply my exponents, which would just give me y. And then on the right side, 3 times 1/2 would be 3/2. So that's going to give me a y equals kind of setup. So then from there, I'm going to take the derivative. The derivative of this is going to be 3/2 x to the 1/2 power. Okay, so now I can go forward with setting up my integral, and my integral is going to go from 1 on the x-axis to 4 on the x-axis. And my arc length formula is 1 plus the derivative squared, and then dx on the outside. From here, your job is just to solve this integral. So I think probably the best approach would be to try to simplify inside the radical first. So 3/2 squared is 9/4. X to the 1/2 squared would just be X. Okay. Remember, we cannot integrate a radical with all this stuff inside of it. So in order to move forward from here, we're going to have to do U substitution. So let's make all this stuff on the inside into U. And then we'll take the derivative. So that would give me just 9/4. And then we solve for du. So this would be 9/4 dx. Except in this case, we want to solve, oh wait, I forgot. We're solving for dx instead of du because that's what we're plugging in for. So other way. So this is going to be dx is equal to 4/9 du. Okay, so all of this here is going to go in place of dx, and then all this u values or stuff is going to go in place and change into u. So my integral is going to look like 1 to 4, radical u, and then we have 4/9 du. Obviously that order is not great. So we'll move the 4/9 to the front. And I think what I'll also do is instead of radical u, I'll call that u to the 1/2 power. Now it's finally looking like something that I can integrate. So we can go ahead and take the antiderivative of u to the 1/2. So that would be, let's see, add 1 to the power, divide by that power. So it's going to be 2/3 u to the 3/2, I believe. And evaluate from 1 to 4, except I think I'm going to stop right here and change the 1 to 4, because right now the 1 and the 4 are both x values, and I've got an integral that's in terms of u. So I think what I'm going to do is stop and change these to terms of u so I can go ahead and just plug them in. So the way that you do that, remember, is you take the number and you go up to your u equation and you plug this in for x. So I would do 1 plus 9/4 times 4. Which would give me 10. And then 1 plugged in. So 1 plus 9/4 times 1 would be 9/4 plus 1, so 13/4. Okay, now I'm going to do evaluating. So I'm going to plug in, and I think I'm going to multiply this fraction at the same time. So this fraction would be 8/27. Plug in 10. And then plug in 13/4. Okay. All right, we want to simplify. So let's see. This may be helpful to stop and rewrite that like 10 to the 3/2 is the same as the square root of 10 to the 3rd power. So I think I'm going to write both of those that way. Okay, simplify, keep going. 10, let's see. This would be equal, I could take out 2 10s, or a 10, so this would be the same as 10 radical 10. And then over here we would have 13/4 times radical 13/4, except the square root of 4 is 2. So I think I could make this denominator an 8, because the 2 could come out. And then make this just radical 13. Try to avoid decimals. All right, best I can do, this is a really ugly answer, but best I can do is 80 radical 10 over, actually minus 13 radical 13 all over 27. If you want, you can type that in as a decimal just to get an idea of what the arc length actually is, a better idea. Okay, let's try another one. So on this slide, I have the arc length formula for you again, except it has been transformed slightly. So if you have a curve where the variables are interchanged, where it's x equals all the other stuff, what you can do is you can integrate, you can change your formula as well. So instead of f prime of x, you could do the function but in terms of y, the derivative in terms of y, or dx by dy. So you can just kind of flip the script. You will notice your interval goes from c to d. It's the same thing as going from a to b, but on the y-axis. Okay, so let's try one. This one would be a perfect candidate because x is alone in the equation instead of y. So I could follow the new formula. I'm going to take dx dy, which just means take the derivative of x with respect to y. So that would be 2y. And then I am going to solve that for dx. Actually, I don't need to do that yet. Okay, let's plug it in. It says we're going from 0, 0 to 1, 1. I would use 0 and 1 in my integral because those are the y values from point to point. And then arc length formula gets plugged in. So 1 plus your derivative squared with dy on the outside, since everything is now in terms of y. Okay, the next move is kind of get it ready to integrate. So 0 to 1 is still my interval. I think I'm just going to quickly clean this up and call it 4y squared. Okay. At this point, you could try u substitution, but u substitution is not going to work real great. So there is a way to solve this integral by hand. It is awful and messy and not worth wasting time on, to be quite honest with you, because you are not going to have to do that in this class. So from here, I would say once you get it set up, use a calculator to solve or evaluate this integral from here. If we ever have time in class, next time I see you, I will show you how to do this. It's called trig substitution is how you would do this by hand, but we don't have time for that. So I will give you the rational number answer, where you would likely have a decimal for this, and that is totally fine. So if you were to do it by hand, this is the arc length solution that you would get. Okay. Example 3. Set up an integral for the length of the arc of the hyperbola xy equals 1 from the point 1, 1 to the point 2, 1/2. So we're going to start by going over here and let's solve the equation for y, just so we have something easy to deal with. And remember that this is the same as x to the negative 1 power. And then we have to integrate so that we can plug this into our arc length formula. So if I integrate, I would make the negative come to the front and subtract 1 from the power, which would make this turn into negative 1 over x squared. All right, so we're still in terms of x this time, so we're using x value to x value when we set up our integral. And we need the square root of 1 plus, and it's negative 1 over x squared, quantity squared, with dx on the outside. All right, why does it say set up the integral without solving it? Well, that's because the square root sign in your arc length formula often leads to an integral that is very difficult or even impossible to evaluate explicitly. Sometimes we have to just be cool with finding an approximation to the length of the curve, or using a calculator to help us. So if this problem said just set it up, which I have seen these on the AP exam, you could be you could be done at the step that you have currently, or you could just do some simple algebra and, like square the fraction in this case. Either one is totally fine with me if the directions don't specify otherwise. Okay, so what we were just working on is finding the arc length measurement. But at sometimes it will be more helpful to create an arc length function. And what that means is that you will have an answer that is an equation that represents the arc length at any point in time on that curve. So, let's say we have a parabola and we want to evaluate the arc length from 0 to 1. And then for some other situation, we want to evaluate the arc length from 0 to 5. So it's creating a function to represent arc length kind of allows you more flexibility so that you're not starting from scratch every time. Okay, so this is just a geometric interpretation of what arc length is. We kind of already looked at this. So this is just reiteration of something we've already seen. Let's go to an example so I can show you what arc length function means. Find the arc length function for a curve y equals x squared minus 1/8 ln x, taking point 0 as 1, 1 as the starting point. So you have a starting point, and we're going to write a function that describes the arc length from any point thereon. Well, as in any arc length problem, we start with finding the derivative. So we need to find dy dx, and in this problem that would be 2x minus 1/8 times the derivative of ln, which is 1 over x, and I'm going to simplify that to 2x minus 1 over 8x. Okay, so we're going to set this up. In the previous slide, it did say that the arc length formula or equation is usually called S of x. And when you do your integral, it's going to have your starting point down here, and then up here will just be the variable x. Okay? Now, to stay within the rules of math, we do have to change our variable because x is already a letter established up here in the integral. So we're going to change these while we're still plugging them into something different. I'm just choosing t. I think that's the letter of choice in the formula as well. So I'm going to use t when I plug in my derivative. That means this would have to be dt. All right. We are going to still go through and simplify. Now, in this case, you're going to have to be super careful. Simplifying means you're going to be squaring this binomial. So remember the shortcut is square the first term. The middle step is multiply these two terms and double it. When you multiply 2t times negative 1 over 8t, you get negative 2t over 8t, but that reduces to just negative 1/4, okay? But we want to double that value. So double negative 1/4 becomes negative 1/2. And then the last step is to square the last term, which would be 1 over 64t squared. Okay? I see some like terms. Yes, I know this is tedious. We haven't even gotten to the integrating part yet. I see some like terms. I think I'm going to rearrange a little bit too. Now, I'm going to rearrange in a way that's probably weird for you guys. I'm going to put the 1/2 in the middle. So the reason I'm going to put the 1/2 in the middle is because if you look at the way we squared this binomial from the beginning, right? When we squared the binomial, we got a squared term, the middle term was a number, a constant, and then the last term was a fraction with variable on the bottom. I'm going to set it up so that I have the same sort of deal. Squared term, constant value, fraction with my variable. Because my next step is going to be to factor that. This is the most challenging thing you're going to have to do in this entire section, is factoring these weird trinomials here. Okay? Remember that there is a trick for factoring. The trick for factoring is that you can take the square root of the first term, so 2t, and you can take the square root of the last term, which would be 1 over 8t. And in this case, we would want a plus sign between because our middle term is positive. The whole reason why we wanted to factor that down in this question is because the square root and the squared will cancel each other out. So that's going to leave me with something that is so much nicer to deal with, considering I actually do have to integrate this thing. Look at that. Square root's gone. Now I have something normal-ish looking that I can integrate. You could also write it, if you want to, write it as 2t plus 1/8 t to the negative 1 power. All right, here we go. Finally to the integrating step. So integrate 2t, and you would get 2t squared divided by 2. So just t squared. Integrate 1 over 8t, and you're going to get 1 over 8 ln of t. Evaluating from 1 to x. And then we can plug in those values. So plug in x first. And then plug in 1. And simplify. So your function for arc length is going to be x squared plus 1/8 ln x minus 1. So again, what this is this is an equation that will tell you the arc length from the initial point, which was 1, 1, to any point on the curve. So here's a visual for you. If I want to find the arc length from 1 to any other point on the curve, I would just say what that other point is, like 5, whatever you want it to be, and you would simply plug in 5 everywhere that you see an x, and you would get your arc length.